Okay, everyone. So last time we spoke about conjugate priors, and what I'm going to do this time is give an example of a conjugate prior, and then sort of talk more generally how to go about developing or designing conjugate priors. So let's look at an example. Of a conjugate prior. In some sense, we had seen two examples already. When it came to the coin flip, we had a Bernoulli distribution, and we found that the conjugate to that was the beta. We didn't use the word conjugate, but we basically said that the posterior had the same form as the prior, and that was a beta distribution. Then we looked at the more complicated example where we had discrete k options, and then we found that the conjugate prior to that categorical was the Dirichlet distribution. Now we're going to do something sort of as a third example, before we discuss sort of general theory. We're going to discuss a Poisson likelihood, which will take this form. Mu to the Wn divided by Wn factorial e to the minus mu. And this distribution, I believe, is the first time we talk about it. It happens very often in the natural sciences, and it's called a Poisson distribution. So it is a discrete. Let me say a couple of things about the Poisson distribution before sort of writing down a conjugate prior and then writing down the resulting posterior. So the Poisson distribution is a distribution which is normalized, Wn from 0 to infinity. So in other words, it is a discrete distribution where the Wn's can take on any value from 0 to infinity. And if I look to verify that this is indeed normalized, I can basically plug in the expression here. So I'm going to pull out the constant with respect to Wn. I have mu to the Wn divided by Wn factorial. I verify immediately that this is the definition of e to the mu. So e to the negative mu multiplied by e to the mu gives me +1, showing that this is indeed a distribution which is normalized with respect to w, assuming w are integers. Now, where does it pop up in nature? Well, let's think about a birth process that we've talked about quite a bit. If I have some kind of birth rate, let's call it lambda b, and I ask in some time interval delta t, how is the number of birth events, or from what distribution is the number of birth events drawn? Now, the number of birth events is going to be a discrete number. Maybe I've had no birth event, and that's going to be 0. Or I've had 10 birth events, and that's another integer, all the way up to infinity. It turns out, and it can be shown, and it's not that difficult, that if I have a birth process, and I ask about the number, or how the number of births is distributed in some delta t, then I find that this distribution is in fact Poisson distributed. And mu, therefore, here takes the meaning of the birth rate times the delta t. So we can even think of using Poisson processes, for example, not just to talk about birth events, but also to talk about nuclear decay, to talk about photon emissions from excited molecules, to talk about any sort of type of physical process where you have an exponential wait time between events, and you're basically asking how many of those events happen in some unit time. And we will find that that is Poisson distributed. Okay, so now that we've sort of briefly introduced our Poisson distribution, let me go ahead and write down the prior, which is conjugate to the Poisson distribution. And then later we will discuss sort of how to develop or how to design these conjugate priors. So I'm just going to go ahead and write it down, assuming that I had just guessed it. And it's going to be a gamma distribution. And the gamma distribution, like a Gaussian prior, for instance, would have two hyperparameters. Not all distributions have two parameters. Obviously, some distributions have one, and you can have an arbitrary number of parameters. But by chance, the gamma distribution is one of those distributions with two parameters, and we call them alpha and beta. And if I were to write down the gamma distribution explicitly, I have 1 over beta times gamma alpha. Gamma alpha, again, is the gamma distribution, so it's alpha minus 1 factorial by definition. I have mu divided by beta raised to the alpha minus 1 times e to the minus mu over beta. That's mu. That is the gamma distribution. So in other words, it depends on mu to the alpha minus 1, and I have an e to the mu minus beta. Sometimes people call beta the shape parameter, and people call alpha the scale parameter. Just like we have two parameters in the normal distribution, we call one the mean and one the variance. Here we call one the scale and one the shape. So if I were to plot the gamma distribution, this particular one, it might look something like this. The scale will dictate how I decay for large mu values, and the shape will more or less determine when I rise, whether I rise here, whether I rise there, and so on and so forth. So here the shape is alpha minus 1. And typically alpha and beta are both greater than 0. Just like, again, the standard deviation must be greater than 0 in the Gaussian, but the mean could go anywhere from minus infinity to infinity. So hyperparameters typically, the nature of hyperparameters depends on the distribution. And in this particular, for this particular gamma distribution, that's the condition. So let's go ahead and multiply the gamma by the Poisson. Now let's remember, if we have a conjugate prior, then that more or less determines, or more or less dictates, that I should obtain a gamma distribution as my posterior. Just one important thing again, I know this is nitpicky, but I think it's worth emphasizing. My likelihood is a function of the w, and we've already verified that if I integrate over my w, I can verify that my Poisson distribution is indeed normalized. Similarly, if I integrate over my mu, I can verify that my gamma distribution is indeed normalized. In fact, that's where this gamma function and the beta come in. So they may naively, the Poisson distribution, the gamma distribution may naively look similar. Here I have a mu raised to some power, and I have an e to the minus mu. Here I also have an e to the minus mu. I also have a mu raised to some power, but they are completely different distributions. One is normalized with respect to mu. The other one is normal at mu and continuous, mu from 0 to infinity. I should have said that. The gamma distribution only has positive support. While the Poisson distribution itself is normalized with respect to positive integers. So while they look naively similar, they're actually completely different. So let's go ahead and multiply the two together. So if I were to construct, for example, my posterior after collecting a single data point, I remember that I have to multiply the prior by the likelihood. And I don't need to worry about any term that depends on the data, right? I only care about the dependency in terms of the parameters, mu. So let's go ahead and keep all of those dependencies explicit. If I do this, then I'm going to write it down, and I'll explain it in just a second. I will have mu to the w1 plus alpha minus 1 times e to the minus mu times e to the minus mu over beta. And we can ask ourselves the question, where does this form come from? Well, the e to the minus mu came from the Poisson distribution, the e to the minus mu over beta came from the gamma distribution, and this multiplicative algebraic factor mu raised to some power came from a combination. So mu raised to the w came from the likelihood, and mu raised to the alpha minus 1 came from the prior. But if I look at this, what I realize is that this is exactly the same form as the gamma distribution, except that my parameters are now a little bit different. So my prior was a gamma distribution, and it had two hyperparameters, alpha and beta. My posterior is also a gamma distribution, and its parameters are alpha tilde and beta tilde. And my goal is now to be able to find what this alpha tilde and this beta tilde are. If I look hard enough, what I find is that my posterior, I'll write it down and explain in just a second, is alpha plus W1, and then 1 over beta plus 1. So this is my new alpha tilde. This is my new beta tilde. So the posterior, after collecting one data point, takes exactly the same form as the prior. What about after collecting n data points? What would that look like? Okay, well, it's not that difficult. I have W, 1 to n. That's still going to be a gamma distribution, which will depend on mu, alpha tilde, beta tilde. And now let me go ahead and write down what alpha tilde will be. It'll be alpha plus sum from n is equal to 1 to big N. And I obtain that by simply multiplying my n data point likelihood by my prior, collecting all terms just like I did on the last slide, and then verifying what my posterior looks like. And if I were to write down what my beta tilde looks like, it'll be 1 over beta plus n. So what we're basically seeing is that, again, to re-summarize, that the gamma distribution happens to be conjugate to the Poisson distribution. And now the obvious question arises, how did I know that it was the gamma distribution? And how do I find conjugate priors? So that sort of leads us a little bit into the discussion on exponential families. And this will be the exponential families of distributions for the likelihood for which we can find conjugate priors. So let me go ahead and write down a likelihood for one data point that belongs to the exponential family. I'm going to go ahead and write it down, and then I will explain the individual terms. Though there's really not much to explain, it's more of a definition, but just making sure the notation of the definition is clear. So here is a distribution belonging to the exponential family. This distribution is the likelihood, and the claim is that if likelihoods can be written down in this form, in other words, if likelihoods belong to the exponential family, then I will be able to identify a conjugate prior. So what's special about the exponential family? Well, preceding the exponential, you have a function which only depends on w, the data, and then you have another function that only depends on theta, which are the parameters. And then afterwards, the exponential must be written as the sum over terms which are products, and those individual terms depend on the parameters multiplied by the data. So this is of a very particular form, and if my likelihood does not follow this form, then I will not be able to find a conjugate prior. So let's give an example of this just to be very concrete. So the question is, does the Gaussian belong to the exponential family? It does, and let me go ahead and show that. So this is what a Gaussian, this is what a Gaussian likelihood for one data point looks like. So I'm going to write it down as 1 over square root 2 pi nu e to the minus w minus mu squared divided by 2 nu. Nu here is the variance. So the question is, can I rewrite this as in the exponential form? So let me go ahead and try to do that above while keeping all terms clear. Sorry. So first thing I'm going to do with my likelihood is that I'm going to expand it. I'm going to expand what I have in the exponential here. So I'm going to rewrite this as 1 over square root 2 pi nu multiplied by e to the minus mu squared over 2 nu. I'm going to put this in brackets. I'm going to rewrite the rest as e to the w mu over nu minus w squared over 2 nu. Now, if I compare this likelihood to the definition of the exponential family, I can ask myself the question, does my Gaussian likelihood, the only thing I've done is I've expanded the argument of the exponential, does the Gaussian likelihood belong to the exponential family? So let's look at it term by term. This term here is the prefactor that depends on g of theta. What about my f of w? Well, for all intents and purposes, that is 1. I don't have a term that depends on data. In fact, just by definition, there's nothing wrong with saying that 1 over square root 2 pi is f of w, and then g is the 1 over square root variance e to the rest of the stuff. So by convention, there's no difference between those conventions. But for now, by convention, I've lumped in my constant into g of theta. Okay, and now I have an exponential that has 2 terms. So my big K is going to be equal to 2. And in the exponential that has 2 terms, I have 2 terms, one of which depends on the parameters, multiplied by another term which depends on the data. And then to that, I add another term that depends on the parameters, multiplied by another term that depends on the data. So U1, I'm going to go ahead and write it down. U1 is W, and then phi1 is mu over nu. That makes sense. This is the term that depends on the parameters. This is the term that depends on the data. U2, I'm going to call W squared, and then I'm going to lump the constant with everything else, and I'm going to call phi2 1 over 2 nu. So interestingly, when I rewrite the Gaussian, like I said, my k is equal to 2, and I can express the Gaussian as belonging to this exponential family, which suggests that I can identify a conjugate prior for the Gaussian. Now, we already know that a Gaussian multiplied by Gaussian gives another Gaussian. So in fact, the Gaussian is one of those special cases where it's in fact conjugate to itself. But let's go ahead and do something a little bit more complicated and write down the n data point likelihood. So this is for one data point. What would this look like if I had n data points? It's not going to be that complicated. I'm going to have a p of w 1 to n given theta. So again, now just to summarize, I want to write down my likelihood for n data points, but I want to write down the definition of that likelihood as belonging to the exponential family. So I'm going to have a product from n is equal to 1 to n, f of wn, right? So if each of the one data point likelihoods has an f of w, then my n data point likelihood, if I multiply all of those likelihoods out, assuming I have IID data, then I'm simply going to get sort of this product term. I have another term which only depends on the parameters, and that's going to be raised to the power of n. And finally, probably the most important part is that I'm going to end up with a term from k is equal to 1 to big K, phi sub k of theta multiplied by t sub k w1 to n. I need to be a little bit clear by what I mean by t sub k, and let me go ahead and write it out. So t sub k w1 to n is the sum from n, 1 to big N, u sub k, wk. And t sub k has a name, and it's called a sufficient statistic. So let's just look at this for a second and kind of, let's look at this for a second and sort of, again, take in stock what we've written down. We have the term f, which appears now as a product. We have the term g, which is now only depending on parameters, so raised to the power of n. And we have an exponential, which is the sum of two terms. Instead of using my UKs, summing over my UKs in the argument of the exponential, I've rewritten them as a TK, and I've called that a sufficient statistic. So this is what my likelihood would look like for n data points if it belongs to the exponential family. And again, just to repeat, if it belongs to the exponential family, then I can find a conjugate prior, which I'll talk about very shortly. Why are we calling these sufficient statistics? Well, that's kind of interesting. When we collect data, and suppose that we say that the data is drawn from a Gaussian, then there are only two different ways of rearranging the data that will give me important information to be able to parameterize my Gaussian. The first thing will be the mean of the data, and the second one will be the variance of the data. Now, in the way that I've rewritten my my Gaussian as belonging to the exponential family, it may not be the mean and the variance, but equivalently, it could be the mean over nu. I'm just writing down the u1, and here's the u2. And it could be negative 1 over 2 nu. But either way, if I collect data and I know that the data is drawn from a Gaussian, then there's really only two ways that I can rearrange that data in order to generate the parameters that I need to fully calibrate my Gaussian. If I consider third moments, in other words, if I consider kind of my data raised to the third power, then I'll always be able to take that and reduce it to the following two quantities. This is a linear or nonlinear combination of the mean and the variance, and this here is the mean. Or in other words, I can always rewrite it as the mean, or using the mean and the variance. So there's nothing unique contained, therefore, there's nothing new contained in the third power in considering the third power of the data. So we know that a Gaussian has two parameters, and it turns out that in order to calibrate those two parameters, I really just need sort of the mean of the data and the variance of the data. Now, different distributions are going to have different sort of regroupings or rewritings of the data, considerations of the data, in order to be able to parameterize them, and these things are called sufficient statistics. That's what sufficient statistics are. Okay, so now that we've talked about our likelihood, now let's talk about the prior. And let me go ahead and write it down right underneath. The prior, or the conjugate prior, will be g to the eta theta exponential of sum over k from 1 to big K phi sub k of theta of nu k. This is the form that the prior needs to take if, when multiplied by the likelihood, we are to obtain a posterior of the same form as the prior. And we can verify that that's the case by multiplying these two together. In fact, if I multiply the prior by the likelihood, so this is now going to be my posterior. My posterior is a function of theta, so I don't bother about the product of f of w because it does not depend on the parameter. Instead, I get g n plus eta to the theta, and then in the exponential, I get sum of k from 1 to k, 5k theta, and then I get tk w 1 to n, plus nu k, close bracket. So there's a lot of things to talk about right now before we actually look at a sort of concrete, and we're going to look at sort of two concrete examples of identifying conjugate priors at this point. But let's delve into a little bit of the details. First question, how many hyperparameters does my conjugate prior have? Well, all k of them, in fact, are hyperparameters, and this is a hyperparameter. So the hyperparameters are eta and nu 1 to k. So I have k plus 1 total hyperparameters. Great. How do I interpret them? Let's look at what my posterior looks like. And there's something really interesting that arises. Whenever I have n here, I have the eta. So in my n, I have the eta added to the n. So in my prior, if I were to look at my prior and I compare to my likelihood, what I see is that eta is playing the role of the n in the likelihood. So the eta of the prior is playing the role of the n in the likelihood. So then oftentimes we call eta in the conjugate priors a pseudo count. Now, the ability to interpret the hyperparameters is typically not possible unless we have conjugate priors. With conjugate priors, we have sort of this unique ability to be able to interpret what the hyperparameters are. So pseudo count is really important because what it's telling us is that my prior, for example, is worth eta data points. Now, ideally, if I collect 100,000 real data points, then maybe if I make my pseudo count 3, it isn't that bad to assume that my prior opinion is worth the equivalent of 3 data points, while my observation is worth, on the order of 100,000. So eta is interpreted as a pseudo count. What about the nu k's? Well, they are pseudo-estimates. Pseudo-estimates of the sufficient statistics. So if you identify a conjugate prior, assuming that your likelihood belongs to the exponential family, then you would say, for example, if I have a Gaussian as my prior, then I will assume that that Gaussian comes from the equivalent in the prior of 3 data points, and that I have an estimate, a preceding estimate, a prior estimate for my mean, and a prior estimate for my variance, and those are coming from, let's say, 3 data points, right? So all this is possible, this interpretational stuff that we're doing here is all possible when we're working with conjugate priors. So let's go ahead and talk about 2 examples of a conjugate prior. So, or the usage of a conjugate prior. So let's suppose our data is normally distributed, and we know the mean, but do not know the variance. So our goal is to estimate the variance from the data that we collect, knowing what the mean is. So let me go ahead and write down first off the likelihood. Rather than to use the variance, I will use the precision, which is 1 over the variance, as my parameters, and I will rewrite my likelihood as tau n over 2 multiplied by the exponential of minus tau n nu over 2. Here nu I have defined as 1 over n, sum of n from 1 to n, wn minus mu squared. So you may start by asking me, where does this expression come from, this one here? Well, remember, I have a Gaussian likelihood, so just to backtrack for 1 second, I have the product of normals, so I'm going to have the product of square root tau divided by 2 pi. Notice that normally if I had the variance, I would write it out as 1 over square root 2 pi multiplied by the variance. But the precision is the inverse of the variance, so I'm writing it down as the square root of tau divided by square root 2 pi. And then I have an e to the minus tau, wn minus mu squared divided by 2. Okay, now, if I take this product over this entire quantity here, then I have tau raised to the power of the number of data points divided by 2, because I have a square root, so that's where the tau n over 2 comes from. And then I have e to the minus tau, and then I have a sum. If I were to, bring this product in here, this would give me e to the tau and then a sum of all of those n terms. But the data are known and the mu is known, so it's just a number. So I have a number multiplying tau, and I'm calling this number nu. That number could be 2.7, 8.5, but it's going to be a number. So I'm going to put that number, I'm going to call that number nu, and I'm going to stick it in there. So this is now my likelihood. You can ask, okay, well, this is my likelihood given my precision and my mean. So why am I not saying comma mu? Well, the mean is known. The mean is a number. So we never say conditioned on, for example, 2.3, right? We usually condition on, in this particular case, the likelihoods in Bayesian application in terms of the quantities we want to learn, not the quantities that are already known. Okay, so let's go ahead and now, having written and sort of explained our likelihood a little bit, let's go ahead and write down a conjugate prior. So now, in order to write down the conjugate prior, we have to figure out what the f of w is, what the g of theta is, and what the phi 1 and the u1 are. Now, the f of w I can consider to be 1. My g of theta here is tau to the 1/2. Right? So my g of theta is tau to the 1/2. And when I have an n data point likelihood, it's g of theta raised to the n, so it's tau to the 1/2 raised to the n. And what about phi 1 and u1? Okay, well, phi 1 is the one that depends on the parameters. So that's just tau. And my u1 is negative mu over 2. So now that I've written all this down, I can go ahead and write down my conjugate prior. So my conjugate prior, p of tau, is going to have the form tau raised to the alpha minus 1 times the exponential of minus tau over beta. The fact that I'm rewriting it as alpha minus 1, I'm writing it as 1 over beta, instead of, for example, tau raised to some, let's call it some constant, and the exponential of tau multiplied by some other constant, right, sort of to be the pseudo count and the pseudo estimate of the point statistic, is a matter of convention, because I want my p of tau to look like a gamma distribution. So I'm specifically writing my pseudo count as alpha minus 1. Okay, now if that's true, then we already know this distribution. It's a gamma distribution, and when I multiply it by this likelihood, then I should obtain a gamma distribution back. So I think one thing that's difficult with this example is the fact that, again, its dependency on tau, we need to be careful about its dependency on tau, because in the end we want to develop a posterior on tau. So we have to sort of keep track of the normalization in my likelihood. So if I were to multiply the prior by the likelihood at this point, I'll obtain a tau raised to the n over 2 plus alpha minus 1. That's the, that's the count, and this is sort of the pseudo count contribution. And then I have an e to the minus tau nu over 2 plus beta inverse. And now I have found sort of what my alpha inverse is and what my beta inverse is. And I know that this is a gamma distribution which depends on tau with parameters alpha tilde, beta tilde, and I know what beta tilde and alpha tilde are. So this is an example of me constructing a conjugate prior to the likelihood, a Gaussian likelihood, assuming the mean is known and the variance is unknown. The next sort of obvious example we can do is the opposite case, where we know the variance, but we don't know the mean. So let's go ahead and do that very simple example, which is the conjugate prior, assuming known variance and unknown mean, and of course still assuming that the data itself is drawn from a Gaussian. So let me go ahead and write down my likelihood. First big difference is that I'm not conditioning on tau, because tau is known. I'm conditioning on mu. And that's going to be proportional to the exponential of the precision divided by 2, or 1 over 2 times the variance. And then I have sum over n from 1 to n, wn minus 2 squared. We can ask the question, what about the tau to the n over 2? We saw that before. Why don't we see that here? Well, tau is known, and our goal eventually is to construct a posterior on mu. So I don't care about terms, prefactors, which are constant with respect to the thing that I care about. And the thing that I care about is mu. Okay, well, what about the prior? Okay, well, at this point we can do this example a little faster and basically say that, we can write down our f of w, or g of theta, our phi1 or u1, or phi2 or u2, and then basically decide that, based on this, that our prior will also be a normal distribution. And it's going to have two hyperparameters, a mean and a variance. So if I go ahead and I multiply this normal by that normal, then I should be able to identify or be able to find that my posterior is another normal, but with these kind of renormalized hyperparameters for the mean, the xi, and psi for the variance. If I were to go ahead and write it down, then, it basically, how would I determine them? Let's just say how I determine them before I write them down. Again, I multiply this by this, but if I multiply this by this, it doesn't look like a Gaussian in mu. It just looks like a product of two Gaussians in mu. So I have to sort of expand out the exponentials, and sort of recomplete the squares to make it look like a single Gaussian in mu. And if I do that, then I find that xi tilde is w hat, which I'll define in a second, n tau plus xi psi divided by n tau plus psi. And psi tilde is 1 over n tau plus psi. Okay, and w bar is simply the sum of the normalized, 1 over n, sum of the data. I shouldn't say normalized, it's the sum of the data divided by n. Okay, let's just make sure that I know my xi tilde and my psi tilde. So w bar is the sum of my data. That's a number, I know that. Big N is the number of data points, I know that. Tau is the precision. I'm assuming that the variance is known. I can invert it, I know the precision. Xi and psi are hyperparameters of my prior, I know those. So xi tilde is a number, like, it's a mean, so maybe it's like negative 2.4. And psi tilde, same thing, I know all these quantities. It's another number, and that number is going to be something like, again, it's going to be positive, so maybe 12.6. So now I can literally just plot my posterior over my mean, my mu. And that kind of summarizes the sort of simpler discussion on identifying conjugate priors conjugate to the variance, conjugate to the mean, and it does leave one last little point, which is identifying joint priors on the mean and the variance. But tell you the truth, these examples actually happen very rarely, where you have to find sort of priors which are joint on two different variables. Later on, by the time we get to chapter 5, we will be talking about sort of how to draw samples from multidimensional distributions using something like Gibbs sampling. And Gibbs sampling will require sort of the deconstruction of the posterior in terms of single variable, oftentimes single variable functions. And the goal will be to find conjugates to those. So the ability to identify conjugate priors to two variables is not used all that often. It is described in the textbook in case you want to look, but it isn't a common tool that's used in computational modeling, especially as we turn to sort of chapter 5. So at this moment, therefore, I will wrap up sort of the discussion of conjugate priors before we move on to other topics next time. Thank you.